Okay, you guys, here we go. This is Chapter 10, Two Sample Designs. So last week in Chapter 9, we learned how to do hypothesis testing and effect size for one sample designs. Here in Chapter 10, we'll learn how to do hypothesis testing and effect size for two sample designs. So in a two sample test, there are two different groups of scores. The null hypothesis is that both groups have the same mean in the population. So here in Chapter 10, for each problem, there are going to be two groups of scores, and the null hypothesis will always be that the mean in the two groups is the same. One of the hardest things for students to sort out here in Chapter 10 is the two different types of two sample tests. So we have two sample tests that are called paired samples test, and then we're also going to have two sample tests that are called independent samples test. So up first, we're going to take a look at paired samples test. When you move on to research methods next semester, you might hear these tests referred to as within subjects designs. In a paired samples test, you have two groups of scores, and the two groups of scores are related or paired. So in a paired samples test, every X score has a corresponding Y score. The paired samples problems might remind you a little bit of correlation in Chapter 6. In Chapter 6, when we were talking about correlation, we also had pairs of X and Y scores. The second type of a two sample test is called an independent samples test. So again, when you move on to research methods next semester, you might hear this referred to as a between subjects design. When you're dealing with an independent samples test, you have two groups of scores, but the scores in the two groups aren't related to one another. There is no pairing of scores between the first group and the second group. So in a paired samples test, you have pairs of X and Y scores. In an independent samples test, you have two groups of scores that aren't related, aren't paired. In the first half of Chapter 10, we're going to focus on learning how to conduct a paired samples test. Up first, we need to distinguish between the three different types of paired samples test. The first type of paired samples test is called a repeated measures or a pre-test post-test design. In a repeated measures design, the pair of scores come from the same subject, the same individual, on different trials of the experiment. So one of the most common forms of a repeated measures design is a before treatment and after treatment design. So for example, if we wanted to study the effects of a new depression medication, we could recruit people who struggle with depression. We could measure their depression score before they get treatment. We could measure their depression score again after they get treatment, and that would create a repeated measures or a pre-test, post-test design. So in this case, the X score would be the patient's depression score before treatment, and the Y score would be the patient's depression level after treatment. The second type of a paired samples test is called a related samples or natural pairs design. So in a related samples or natural pairs design, the scores are paired before research. So the two scores come from different people who have some relationship outside of the research study. So two common examples of related samples or naturals pairs would be husbands and wives or fathers and sons. So in this paired samples design, the X score would belong to the husband, the Y score would belong to the wife. Or the X score would belong to the father and the Y score would belong to the son. The point here is that the X and Y score have to stay together because the two people who contributed these scores represent a natural pair, two people who have a relationship outside of the research study. The third type of a paired samples design is called a matched pairs design. In a matched pair design, the pairs are put together by the researcher. They're matched on some third variable that might affect the dependent variable. So let's suppose we have a new cholesterol medication that we want to test. Suppose the researchers who develop the medication are concerned that the medication might work differently for people in different weight categories. So one thing they could do, instead of just testing people in general, they could create matched pairs based on weight at the outset of the study. So for example, they could find two people who both weigh 150 pounds. They could find two people who both weigh 175 pounds. They could find two people who both weigh 200 pounds. Those sets of people are called matched pairs. Then the researcher would randomly assign one member of each pair to the treatment versus control group. So if there were two people who both weighed 150 pounds, the researcher would flip a coin. One of those people would get the new cholesterol medication and the other one wouldn't. So for each matched pair, the researcher would randomly assign one member of the pair to get the treatment and one member of the pair would not get the treatment. If at the end of the study, the groups are different after treatment, it's not a function of the third matched variable. So in this case, if the people who got the cholesterol medication have lower cholesterol levels than the people who didn't get the medication, we can attribute it to the medication itself, or at the very least, we can rule out the idea that weight played any role in this difference between groups. Next, I'm going to teach you how to conduct a paired samples test. So up first, we'll have to write the null hypothesis and the alternative hypothesis. The null hypothesis in a paired samples t-test is that the mean on x and the mean on y will be the same. So the null hypothesis is always that there is no difference between the two groups. So here, H0, the null hypothesis, is that the mu sub x is equal to mu sub y. The mean on x will be equal to the mean on y. The alternative hypothesis will always be that mu sub x is not equal to mu sub y. So in other words, the null hypothesis is that the two groups have the same mean, and the alternative hypothesis is that the two means are different. So in other words, here for a paired samples t-test, we will always have a not equal to sign in the alternative hypothesis. We will always be doing a two-tailed test. Here, we don't care about the direction of the difference, we just want to know if there is a difference. To calculate the degrees of freedom for a paired samples t-test, you're going to take n and subtract 1. In a paired samples t-test, n is the number of pairs of scores. This might remind you of correlation, where again, n was the number of pairs of scores. To calculate the observed value of t for a paired samples t-test, we'll use this formula, x bar minus y bar divided by s sub d bar. You'll probably remember x bar. X bar is the sample mean on x. Y bar is the sample mean on y. So x bar and y bar, you've calculated them before, and the calculation is very straightforward. So the new term here is s sub d bar. So here in the denominator of the t observed value, we have to learn how to calculate this new term, s sub d bar. This term is called the standard error of the mean difference. So the standard error of the mean difference, s sub d bar. To calculate the standard error of the mean difference, s sub d bar, we're going to take s hat sub d and divide by the square root of n. Again, n is the number of pairs of scores. Capital letter D is the difference score. You'll calculate the difference score by taking each x score and subtracting its corresponding y score. So capital letter D is the difference score. We'll calculate the difference score by taking each x value and subtracting the corresponding y value. S hat sub d is the standard deviation of the difference scores. So S hat sub d is the standard deviation of the difference scores. I'm going to put the formula up next. I promise you it's the same two formulas that I showed you to calculate a standard deviation back in chapter 4. If you don't remember how to calculate a standard deviation, you might want to go back to chapter 4 now and refresh your memory. The formula, when I put it up, it'll be the same formula, but instead of calculating the standard deviation of x, which is what we were doing in chapter 4, now we'll be calculating the standard deviation of d. Other than that, the formulas are the same. The formula on the left is the one that we call the deviation score formula, or the definitional formula. This is the one that I taught you during class in chapter 4. So here we would calculate the standard deviation of the difference score, S hat sub d, by taking the sum of d minus d bar squared, dividing by n minus 1, and taking the square root. The alternative formula is on the right. This one is called the computational formula. To calculate the standard deviation using this formula, you will take the sum of d squared, subtract the sum of d quantity squared divided by n, and then divide that whole term by n minus 1. Then don't forget to take the square root. The last formula that you'll need here in order to conduct the paired samples test is the formula for the effect size index, d. So lowercase letter d, the effect size index, we'll calculate it by taking x bar minus y bar, the mean on x minus the mean on y, and dividing by s hat sub d, the standard deviation of the different scores. Now we have everything that we need to conduct a paired samples test. So next we'll go to an example. The example that I'm going to use of a paired samples test came from one of the groups in my research methods class. They wanted to answer the question, does studying with loud music affect the number of math problems that people can solve correctly? So 2 of the students in this group thought that they worked better when it was noisy. The other 2 people in the group thought that they could study better when it was quiet, so they decided to use this as their research question. I'm going to show you the data for 9 students. So here's data for 9 students. All 9 students were asked to solve math problems in 2 different conditions. They solved math problems when it was quiet, and they solved math problems when it was noisy. So here I have called the X scores the number of math problems when it was quiet. I've called the Y scores the number of math problems solved correctly when it was noisy. So if you look at student number 1 solved 18 problems correctly when it was quiet and 12 problems correctly when it was noisy. Student number 2 solved 21 problems correctly when it was quiet and 21 problems correctly when it was noisy. Student number 3 solved 19 problems correctly when it was quiet and 16 problems correctly when it was noisy. So this is a good example of a paired samples test. Each X score has a corresponding Y score. It's a repeated measures example because the 2 scores, the pair of scores, the XY pair, come from the same person. So here we have 9 people who contributed both an X score and a Y score. In this example, the null hypothesis is that the mean in the quiet condition will be equal to the mean in the noisy condition. So here, mu, the mean, represents the average number of math problems solved correctly. I've decided to use quiet and noisy as my subscripts instead of using X and Y. It helps me remember which problem I'm working and what the 2 groups are. So here, the null hypothesis would be written this way. Mu sub quiet equals mu sub noisy. The average number of math problems solved correctly when it was quiet will be equal to the average number of math problems solved correctly when it's noisy. As is always true, the null hypothesis is that there is no effect. In this case, no difference between the 2 groups, no difference in the number of math problems solved correctly when it was quiet versus noisy. The alternative hypothesis will be that mu sub quiet is not equal to mu sub noisy. So a 2-tailed hypothesis. Maybe that people can solve more math problems correctly when it's quiet. Maybe people can solve more math problems correctly when it's noisy. Here we're looking for a difference either way. So the null hypothesis says that these 2 means will be the same. The alternative hypothesis says that these 2 means will be different. So we're walking through the steps of the hypothesis testing procedure now. So in step 1, you have a substantive question. I gave you the substantive question. The question was, can people solve the same number of math problems correctly when it's quiet versus noisy? Step 2 of the hypothesis testing procedure is to set up your null and alternative hypotheses. We've just done that. Here in step 3, you choose the appropriate test statistic. Here in Chapter 10, the appropriate test statistic will always be t. In both Chapters 9 and 10, the test statistic will be t. Next week in Chapter 11, we'll learn a new test statistic, capital letter F, but here in Chapter 10, the appropriate test statistic will always be t. The next step in the hypothesis testing procedure is to choose an alpha level. Most of the time, in most research studies, we choose an alpha level of 0.05. Hopefully, at the end of Chapter 9 last week, you understood why people might sometimes increase or decrease the alpha level based on the type 1 and the type 2 errors. Here, as in most studies though, I'm going to choose an alpha level of 0.05. I can't see a good reason to increase or decrease the value of alpha. To calculate the degrees of freedom here, I'm going to use the formula n-1, where n is the number of pairs of scores. Here we collected data for 9 students. 9 students contributed 2 scores, a quiet score and a noisy score. So here in this case, n is 9. There were 9 students, which means we have 8 degrees of freedom. Now I can look up the critical value of t in the table in the back of the book. So go to your t table, look across the top of the table, make sure you're in the row for a two-tailed test. Whenever we use a not equal to sign in the alternative hypothesis, that means we're doing a two-tailed test. If you want to draw the graph, it would look like this. Don't forget to label the axis though, t. So this is the t distribution. The t distribution is always centered at 0. So using the table in the back of the book, look in the row for a two-tailed test, then find the column that corresponds to an alpha level of 0.05. Here, the degrees of freedom, we had 9 students, so n was 9, so we have 8 degrees of freedom. So when you look in the t-table, you should find this number, 2.306. Because it's a two-tailed test, I'm going to label the t critical value here and here. So on the upside of the distribution, the critical value of t is 2.306. On the lower side of the distribution, the critical value of t is negative 2.306. What this means is if our observed value of t is somewhere in between negative 2.306 and positive 2.306, we will retain the null hypothesis. But if our observed value of t is greater than 2.306 or less than negative 2.306, then we will reject the null hypothesis. So the next step in the hypothesis testing procedure is to collect data and compute the observed value of the test statistic. So I'm going to show you the data again. Here you have the X scores and the Y scores for 9 students. The next thing that you would do is calculate X bar and Y bar, the mean on X and the mean on Y. Take a few moments now, maybe pause the video, and calculate X bar and Y bar. If you calculated X bar correctly, you should have gotten 18.89. So the average number of math problems solved correctly when it was quiet was 18.89 problems. If you calculated Y bar correctly, you should have gotten 16.89. So the average number of math problems solved correctly when it was noisy was 16.89 problems. The next thing that we're going to do is create a new column labeled D for difference score. To calculate the difference score, you're going to take the X score and subtract the Y score. So here, for student number 1, the X score is 18, the Y score is 12, so the difference score is going to be 6. For student number 2, the X score is 21, the Y score is also 21, so the difference score, 21 minus 21, is going to be 0. So create a new column here, label it capital letter D at the top, and calculate the difference score for each of these 9 students. So for each student, take the X score and subtract the Y score. So for student number 1, it's 18 minus 12. The difference score is 6. For student number 2, it's 21 minus 21. So the difference score is 0. Okay, so when we go to this next slide, Let me walk you through it. Here, we have the original data that I gave you. So for 9 students, their X score and their Y score, how many math problems they solved correctly when it was quiet, how many math problems they solved correctly when it was noisy. Down here, at the bottom of each column, I've labeled X bar and Y bar. So we just calculated these 2 numbers. So the average number of math problems that people solved correctly when it was quiet was 18.89. The average number of problems that people solved correctly when it was noisy was 16.89. So in other words, people solved more math problems correctly when it was quiet than when it was noisy. So I asked you to add this 3rd column and label it D for difference score. So here for student number 1, their number of math problems solved correctly when it was quiet was 18. Number of math problems they solved correctly when it was noisy was 12. So 18 minus 12 is 6. The difference score for student number 1 is 6. In other words, this person solved 6 more math problems correctly when it was quiet compared to when it was noisy. So if you look at student number 2, their difference score is 0. 21 minus 21 is 0. For student number 3, their difference score is 3. 19 minus 16. For student number 4, their difference score is 5. 21 minus 16. For student number 5, the X score is 17 and the Y score is 19. 17 minus 19 is -2. This is our first negative difference score. The first 4 students all solved more math problems correctly when it was quiet. So when you took the quiet score and subtracted the noisy score, you got a positive number. Student number 5 actually solved more math problems correctly when it was noisy than when it was quiet. So the fact that this person's difference score is negative demonstrates that for this student, the Y score was higher than the X score. For student number 6, the difference score is 1. 20 minus 19 is 1. For student number 7, the difference score is 2. 18 minus 16 is 2. For student number 8, the difference score is -1. And for student number 9, the difference score is 4. So the next thing that we're going to do is we're going to calculate D bar, the mean difference score. So we're going to add up all of the D scores, all of the difference scores, and divide by how many there are. So when I add 6 plus 3 is 9, plus 5 is 14, minus 2 is 12, plus 1 is 13, plus 2 is 15, minus 1 is 14, plus 4 is 18. 18 divided by 9 scores is 2. So D bar, the mean difference score, is 2. You'll notice that D bar is also X bar minus Y bar. So X bar is 18.89, Y bar is 16.89. So D bar is 2, meaning on average, people solved 2 more math problems correctly when it was quiet versus noisy. So there are 2 different ways to get this number. I can add up the difference scores and divide by how many there are. I can also take X bar and subtract Y bar. Either way, I'm going to get D bar equals 2. So the next column, D minus D bar. This column is called the deviation scores. So this should start, hopefully this reminds you of doing a standard deviation problem. So D minus D bar, let me clean this up a little bit. All right. Excuse me. So this column labeled D minus D bar, these are the deviation scores. So to calculate the deviation score, D minus D bar for student number 1, I'm going to take this person's difference score, which is 6, and subtract D bar, which is 2. So 6 minus 2 is 4. So the first student's deviation score is 4. The second student's difference score is 0. So 0 minus 2, D bar is still 2. So the second person's deviation score is -2. So I'm taking each student's difference score, their D score, and subtracting their mean difference of 2. So 6 minus 2 is 4. 0 minus 2 is -2. 3 minus 2 is 1. 5 minus 2 is 3. -2 minus 2 is -4. 1 minus 2 is -1. 2 minus 2 is 0, of course. -1 minus 2 is -3. And 4 minus 2 is 2. So this column, these are called the deviation scores. And I calculate each deviation score by taking the difference score and subtracting the mean difference, D bar. If I calculated the deviation scores correctly, they should add up to 0. So add up all the scores in this column and make sure that they add up to 0. Looks like they do add up to 0, so that gives me confidence that I'm working the problem correctly. And then the last column here, this column is called the squared deviations. So for each number in this last column, I'm going to take the deviation score and square it. So the first deviation score is 4, so when I square that number, 4 times 4, of course, is 16. -2 squared is 4. 1 squared is 1. 3 squared is 9. -4 squared is 16. -1 squared is 1. 0 squared is 0. -3 squared is 9. And 2 squared is 4. So this number is the sum of the squared deviations. If you add up all of the numbers in this last column, you should get 60. That's the number that we need to calculate the standard deviation. So the sum of the squared deviations for this problem is 60. This is the number that we're going to need in order to calculate the standard deviation. Okay, so now we can calculate S hat sub D, the standard deviation of the difference scores. So I'm using the deviation score formula or the definitional formula. In order to use this formula, I need the sum of the squared deviations in the numerator. So that's the 60 that we calculated on the previous slide. So in this example, the sum of the squared deviations is 60. I'm going to divide the sum of the squared deviations by n minus 1. In this example, n is 9, so n minus 1 is 8. So S hat sub D, the standard deviation of the difference scores, is 60 divided by 8, and then take the square root. So it comes out to 2.74. Make sure you can get that number. All right, now that we have the standard deviation of the difference scores, S hat sub D, we can calculate the standard error term S sub D bar. So we're going to take S hat sub D, the standard deviation of the difference scores, which is 2.74, and divide it by the square root of n is 9. Excuse me. So 2.74 divided by the square root of 9, which is 3, comes out to 0.91. So now we have everything that we need in order to calculate the observed value of the test statistic. So T observed is x bar minus y bar over the standard error S sub D bar. So here it's 18.89 minus 16.89 divided by the standard error term 0.91. So the observed value of t for this problem is 2.20. This is the number that we're going to need in order to make our decision about whether to reject or retain the null hypothesis. So the last two steps of hypothesis testing, step number 7 and step number 8, are to draw your statistical conclusion and your substantive conclusion. In order to draw the statistical conclusion, you want to compare the observed value of the test statistic to the rejection region. So in this problem, when we set up the rejection region, we decided that we would reject the null hypothesis if our observed value of t was greater than 2.306 or less than negative 2.306. In this case, our observed value of t was 2.20, so our observed value of t is not in the rejection region, which means we're going to retain the null hypothesis. The null hypothesis in this example was that the average number of math problems that people could solve correctly would be the same in the quiet and the noisy conditions. We're retaining that null hypothesis, so our substantive conclusion is that there is no significant difference in the number of math problems solved correctly between the quiet and the noisy conditions. One logical question at the end of this hypothesis test is, do you think that the sample size in this problem had anything to do with the outcome of the significance test? So one way that you can address that question is by calculating the effect size index D. So in this problem, the effect size index D, you would take x bar minus y bar and then divide by the standard deviation of the difference scores. So here it would be 18.89 minus 16.89 divided by 2.74. So the effect size index D comes out to 0.73. If you remember our guidelines for small, medium, and large effects, 0.2, 0.5, and 0.8, here our effect size index 0.73 would be called medium to large. So when we put the significance together, the statistical significance together with the effect size here, it does suggest that the reason we retained the null hypothesis in the hypothesis test is that the sample size was small. We only studied 9 students. Hopefully you remember from chapter 9 that if you increase the sample size, you're more likely to reject the null hypothesis and get a statistically significant result. Here, if we had calculated the effect size and it was very small, less than 0.20, for example, we'd say we may have retained the null hypothesis because there really is no difference between the noisy condition and the quiet condition. But here with this medium to large effect size, it's a suggestion that if we went back and did the hypothesis test again with a larger sample, we would have rejected the null hypothesis. In that case, to draw the substantive conclusion, we would compare the two means, x bar and y bar, and we would word the substantive conclusion consistent with the difference in those means. In this example, the average number of math problems solved correctly in the quiet condition, 18.89, was higher than the number of math problems solved correctly in the quiet condition. So if we had rejected the null hypothesis in this problem, then we would have worded the substantive conclusion. Students solved significantly more math problems when it was quiet than when it was noisy. So again, one of your challenges will be trying to put together the statistical significance and the practical significance. This is a good example where the sample size is small enough that we may have retained the null hypothesis even though there really is a difference. And the fact that the effect size is medium to large suggests that in a real study we would have wanted to go back and taken a larger sample in order to demonstrate this.